The purpose of this video is to introduce the concept of persistence length in the context of molecular objects. But first, let's start by doing a recap of a few concepts we've already talked about. Our starting point is the Brownian motion of a free particle in solution. As the solvent molecules hit the particle from all sides, the solvent molecules being the black dots in this case, the particle moves in a random walk through the solution, and the average distance moved in one direction is given by the diffusion coefficient. So, the average of the square displacement is equal to 2 times the diffusion constant times the time. The magnitude of the diffusion coefficient itself is determined by the thermal energy of the solvent, kT, as well as the viscous drag the particle experiences. And this is the Einstein relation we've also talked about previously. So in other words, the higher the diffusion coefficient, the more the particle will move. Now let's imagine rod-like structures, such as a microtubule, for instance, in a buffer solution. The water molecules will hit the structure and push it around. This is diffusion, as we said, but if the structure is flexible, it will deform a little in response to each push. So if we place ourselves at a certain spot of the rod and look at it, each successive piece of the rod may be bent a little to the left or to the right relative to the previous piece. Essentially, the direction vector performs a random walk. The small changes in direction add up after some distance, but the mathematical description is a bit more complicated than for diffusion. A neat formula would emerge, not if we average the square of the change in the angle, but if we average the cosine of the change in the angle for a given distance L from the starting point. So what we have to do is to go along the rod, measure the angle change for a given distance between the point where we stand and the point which we look at, as shown in this figure. Then we calculate the cosine of this angle and take its average. To do so, we can repeat this calculation at different points on the rod we are actually following, as shown in the following small animation. For instance, if the change in the angle is -1 degree, then 2 degrees, -4 degrees, and then 3 degrees, the cosines are respectively 0.99, 0.898, 0.96, and 0.97. So the average of the cosines is equal to 0.975. If this procedure is repeated for larger and larger lengths, and the average cosines of the angle changes are plotted in a graph, we will find an exponential decay, such as we see in this figure. This exponential function is indicative of a persistent random walk, where the angle changes are random but fairly small, and hence the direction is persistence. The decay constant has units of a length, and it's this decay constant that is referred to as the persistent length. The precise definition of a persistent length is cosine of theta being the angle change of L, equals to exponential L divided by LP being the persistent length. In principle, this procedure can be carried out along any line, and we can determine if the function is an exponential, as well as assign the line a persistent length if it has one. So if this line we're talking about corresponds to a shape of an actual rod-like structure with a certain cross-section and a certain modulus, and the deformation originates from thermal forces, we can define the persistent length with the following formula. Well, here, kT is the thermal energy again, E is the modulus, and I is the second moment of inertia. Note that a large persistent length means less wobbliness of the line. Hence, if EI increases, then the persistent length increases as well, while a large thermal energy kT would decrease this length. It's actually the opposite than what happens for the diffusion coefficient. Let's give a few examples of persistent lengths. According to Wikipedia, an uncooked spaghetti has a persistent length of 100 light years, meaning the thermal fluctuations do not bend it at all over typical distances. If we come back to biological objects that we have talked about in this class, for instance, a microtubule, we can say that a microtubule has a persistence length of about 1 millimeter, meaning it fluctuates only a little due to thermal forces in a cell. On the other hand, an actin filament has a persistent length of about 10 micrometers, and it loses its initial direction rapidly if it is free to fluctuate. The general point here is that thermal fluctuations do not only introduce randomness in the position of particles, but also randomness in the shape of structures at the nanoscale. These shape fluctuations become important if the persistent length is similar to the length of the structure, since the second moment of inertia that appears in the formula of the persistent length, as we saw here, so since the second moment of inertia scales with the fourth power of the radius of the structure, the persistent length scales with the fourth power as well, meaning that as we decrease the size of a structure, the persistent length decreases much faster, and the persistence length approaches the size of the structure as we reach the micro and the nanoscale. Lastly, in order to understand a bit better how persistent lengths play a role in vivo and in actual biological systems, we're going to watch two short videos at the same time. On the left, we have microtubules, and on the right, actin filaments. Microtubules, because they have a persistent length of 1 millimeter, they're able to basically walk in some kind of straight lines, while the trajectories of actin filaments will be modified constantly, and we cannot say that they walk in lines.